Today we're going to look at a question that doesn't seem very interesting or deep, but as we'll see, it is both interesting and deep and surprisingly geometric. And that question is, where can we do fourth grade math homework? And in particular, I mean division with remainder. So let's start with a couple of examples of, well, these fourth grade math problems. And so let's recall that in elementary school, you might have done something like this. 23 divided by 5, and you would have said that that's equal to 4 remainder 3. Because 5 times 4 is 20, that doesn't get you all the way there, so you need this remainder of 3. Or you might have 47 divided by 6 is equal to 7 remainder 5. Or maybe finally, for one more example, you might have 61 divided by 9 is equal to 6 remainder 7. And so what I'd like to do before moving on to generalizing this, I'd like to take these division with remainder questions and write them into multiplication with addition equations. So let's observe, like we said before, this equation 23 divided by 5 is 4 remainder 3 is equivalent to saying that 23 is equal to 5 times 4 plus 3. And then this one right here, where we say that 47 divided by 6 is 7 remainder 5, that's the same thing as saying 47 is 6 times 7 plus 5. And finally, this last one down here is the same thing as saying that 61 is equal to 9 times 6 plus 7. And now what I'd like to do is look at the remainders that we have here, 3, 5, and 7, and compare them with the divisors. So notice that the divisor here is 5, 6, and 9. And notice in each of these cases, we see that the remainder is strictly less than the divisor. And this fact that the remainder is smaller than the divisor is actually an important part of this whole setup. Because when you do division, you're trying to do some sort of simplification of the system. And, well, you should come up with something simpler than what you started with. And the remainder being smaller than the divisor is that measure of simplicity. Okay, so now what I'd like to do is look at these equations right here, most specifically the ones on the right-hand side of the arrow, and observe that we can generalize this into something called the division algorithm. And this division algorithm is not just going to work for positive integers like you would have done in fourth grade, but this is going to work for all integers. And what the division algorithm on the integers says is this. So for all integers a and b, there are integers, I'll call them Q and R, with the following two equations holding, or I guess there's one equation and one inequality. So we can write A as B times Q plus R. So Q is like our quotient and R is our remainder. And look, this is like dividing A by B, getting a quotient of Q and a remainder of R. And then we need this simplification rule, or in other words, we need this fact that the remainder needs to be smaller than the divisor. And so we will impose that 0 is less than or equal to R, which is strictly less than the absolute value of B. So we need the absolute value of B there because we're doing this division algorithm on the integers. And in fact, I would say that the right version of this actually has an absolute value of R here, as we'll see when we generalize this to other spaces, but I'm just going to leave it without an absolute value so it's like a little bit more familiar. And all of this brings us to the big question for this video, and that is, can we extend this idea of the division algorithm, in other words, the division with remainder, to extensions of the integers? Or in other words, when is there division with remainder in an extension of the integers? And so I guess first what we should do is talk about what an extension of the integers is. So to put very briefly, you start with the integers and then you introduce a complex number and you make sure that the new set that you have is closed under addition and multiplication. So some classic examples are the so-called Gaussian integers, which is what you get if you start with the integers and you introduce the imaginary unit I. So we would write this as z adjoin I perhaps, and it's going to be everything of the form a plus bi, where a and b are integers. And now I'd like to just quickly observe here that I is the square root of -1. So that means we have I squared is -1 here. But let's observe that I squared is a solution to the equation x squared plus 1 is equal to 0. So that actually makes this something called a quadratic extension, because what you're doing is you're taking a quadratic equation where the coefficients come from the integers, but it does not have a solution within the integers, and you are adding that solution into a set and then making sure everything is closed under, like I said, multiplication and addition, and I guess subtraction as well. Okay, then maybe the next most common example would be these things called the Eisenstein integers. And so we'll write this as z omega. So this is going to be everything of the form a plus b omega, where a and b are integers. And here, omega is the third root of unity. In other words, omega is the number -1 plus the square root of -3 over 2. Now, you can write that using Euler's formula as e to the 2 pi I over 3 if you'd like to, but we'll leave it like this for reasons that we'll see later. Now, I'd like to quickly observe that this is a solution to x squared plus x plus 1 equals 0. And well, you can check that on your own just by using the quadratic formula or something. It's pretty easy to see that omega is a solution to that equation. So that means, again, what we have here is a quadratic extension. And I guess, like, kind of more generally, you might look at something like this. Z adjoined the square root of -d. And so this would be everything of the form a plus b times the square root of -d, where a and b are integers. And here, well, it's pretty clear that this square root of -d is a solution to a quadratic equation. It's the solution to the quadratic equation x squared plus d equals 0. And just for the purposes of right now, we're going to insist that d is bigger than 0. So that not only makes these all quadratic extensions because they are solutions to quadratic equations, but imaginary or complex quadratic extensions because you are extending by an imaginary number. Or in this case right here, you're extending by a complex number that has a non-zero imaginary part. Okay, so now if we're trying to build something like division with remainder like we had over here, then we need to hone in down here on this equation, which is this important fact that we discussed before, and that is the remainder has to be smaller than the divisor. So the real question here is, if we're dividing, getting a quotient and a remainder, what sort of measurement can we do on the remainder? Well, it turns out that it's not so hard here because all of these things live naturally in the complex numbers. And since all of these are naturally in the complex numbers, we can use the so-called modulus squared as the measurement device. And so just as a brief reminder here, let's say you take z to be any complex number. And so in our setting, we'll have z will come from one of these sets, but here we can do it just with any complex number. And so we might say that z is equal to x plus iy. So those are going to be the real and imaginary parts. And so, like I said, we can take this measurement device to be the modulus squared. So I'll use n to mean norm. As you'll see, that's going to be the terminology that we'll use moving forward. That's the standard terminology in this setting. So the norm of z will be equal to x squared plus y squared. So that's in fact the modulus squared of this complex number z. And I guess you could also observe that that is z times z bar, where z bar is the complex conjugate. And so now we can calculate these norms on arbitrary elements of Gaussian integers, Eisenstein integers, and integers extended by the square root of minus d pretty easily. And so let's do those one at a time down here. So let's observe that the norm of a plus bi, so that's going to be an element from the Gaussian integers, well, that's just simply equal to a squared plus b squared. There's nothing fancy going on there. And then the norm of a plus b omega, well, that's going to be equal to a plus b omega times a plus the conjugate of omega times b. Notice that the only imaginary part in a plus b omega comes from the omega part, so, well, we only have to take the conjugate of that. But now you can multiply this out, and I urge you to multiply this out to see exactly what you get. But in fact, what you get here is a squared minus ab plus b squared. And that's actually going to be bigger than or equal to 0. You can check that using either like a mean inequality or just by the fact that this is the modulus of a complex number in the first place. So that's going to be our norm on the Eisenstein integers. And then here our norm on this extension by the square root of minus d is more in line with the first norm that we saw. This in fact just becomes a squared plus d times b squared. Okay, so now that we've looked at some extensions, more specifically quadratic extensions of the integers, how to measure the size of the elements here, I think we're ready to write down a more general division algorithm that we can explore when this exists and when it perhaps does not exist. Okay, so I think we've motivated the following division algorithm for an extension of the integers. And it goes like this. So for all alpha, beta in one of these extensions, so that's what I'll mean by this box, is that that's just one of the extensions of the integer. So perhaps one of the ones that we had on the board over here before, or a new one that we'll look at later. Okay, so for all alpha, beta in an extension, there should be a q and an r in an extension, where alpha is equal to beta q plus r. So that means that the quotient is q and the remainder is r. And so the divisor is beta, and alpha, that's sometimes called the dividend. And we need this condition right here that says that the remainder is smaller than the divisor using this norm function. And so we've got the norm of r is less than the norm of beta. And, well, we saw before that if we are in one of these imaginary extensions of the integers, then this norm can just be taken to be the modulus squared viewed inside of the complex numbers. Okay, so now let's go up here and do an example in the Gaussian integers z adjoin I. So let's take alpha to be the number 12 plus 23i. And let's take beta to be the number 5 plus 3i. And we're going to run through how you would find a quotient and remainder. So you're going to start by looking at alpha over beta. And maybe before moving on, notice that alpha over beta will not be an element of z adjoin I necessarily. Actually, most of the time it won't. It'll be in some rational extension. And so this is going to be like the rational complex numbers over here. Okay, so let's do the calculation that'll take us all the way there. So we've got 12 plus 23i over 5 plus 3i. And now we're going to do the classic thing that you probably learned in like a high school algebra class, and that is you'll multiply by the complex conjugate of the denominator in the numerator and the denominator so that we have a denominator which is simply a real number. So that's going to be 5 minus 3i in the top and the bottom. Okay, so after doing that product, you'll see that you get 129 plus 69i in the numerator. And then in the denominator, you'll get 36. But now what we can do is split this into a real and an imaginary part, and also put these fractions in lowest terms. So this gives us 43 over 12 plus, that's going to be 23 over 12 times I. And now I'd like to make the following observation, and that is that 43 over 12 lives between 4 and 3. And then also 23 over 12 lives between 2 and 1. I think it's pretty clear that those inequalities are satisfied. And looking at those inequalities will be how we come up with the correct quotient. And then from the quotient, we can construct the remainder. And so let's see, we'll just kind of eyeball this and see, is 43 over 12 closer to 3 or closer to 4? Well, let's observe that 48 over 12 is 4, but 36 over 12 is 3. So this thing is going to be closer to 4. And then likewise, 23 over 12 is pretty clearly closer to 2. So that motivates us to make the following guess at our quotient. And so let's take a quotient, or maybe the first go at a quotient, to be 4 plus 2i, and just see if it works out. Now, let's observe that if we have a quotient of 4 plus 2i, then we can calculate a remainder just by inverting this equation. So let's observe that our remainder will be equal to alpha minus beta times this quotient that we've just constructed. So I'll let you do the calculation there. It is fairly elementary. And what you'll see is you get the complex number minus 2 minus 4i. Okay, good. And so now let's go ahead and write down the whole quotient and remainder equation. So that's going to give us something like this. So we'll have alpha, that's 12 plus 23i. So that's going to be equal to beta, that's 5 plus 3i, times q, that's 4 plus 2i, and then plus the remainder, that's minus 2 minus 4i. So that's our alpha equals beta q plus r equation. And now we just have to check that the norm of this element right here, this remainder, is strictly less than the norm of this element right here, this 5 plus 3i, which is the divisor. So let's check that. And so let's look at this norm of minus 2 minus 4i. So it's pretty easy to see that that number is equal to, what, it's going to be 4 plus 16, so that's going to be equal to 18. Now let's go over here to the norm of 5 plus 3i, and that's pretty easy to calculate as well. That's going to be 25, that's 5 squared, plus 9, that's 3 squared. 25 plus 9 is equal to 34. So here we get 34. And observe that, well, we have it. The norm of the remainder is strictly less than the norm of the divisor, so we're good to go. Now, before we move on to the geometry that is underpinning this whole thing, I'd like to go back over here to our division algorithm and maybe manipulate it a little bit. So let's take this quotient with remainder equation and let's divide both sides by alpha. And so that's going to give us alpha over beta is equal to q plus r over beta. And so dividing by beta will deposit us with that equation pretty easily. Then let's divide both, or I guess I should say all parts of this norm inequality by the norm of beta. And observe that that's going to be 0 is less than or equal to the norm of r over the norm of beta, which in turn is strictly less than 1. But now we can go ahead and take this equation that we've built inside of the rational complex numbers and rewrite it like this. R over beta is equal to alpha over beta minus q. And so notice that this r over beta is this number whose norm is less than 1. But this is like a measurement device. And then this alpha over beta minus q is like the distance that alpha over beta is away from some number in the complex plane. And so what we're going to see now is that viewing it under this light sets up a really nice geometric interpretation of everything that's going on. Here's the Gaussian integer lattice, a square grid in the complex plane. Take any two Gaussian integers alpha and beta. Their quotient alpha over beta lands somewhere in this plane, inside of something that we call a fundamental square. That's a square built by 4 lattice points. Now watch what happens as we move this point around. The furthest it can ever be from a lattice point is 1 over the square root of 2, and that's at the center of the square. That's our worst case. Now if we bring this back to a general position, we measure the distance to each corner of this fundamental square and pick the closest one. We'll call it q. The distance is the modulus of this complex number rho, which is necessarily going to be less than or equal to 1 over the square root of 2, which is less than 1. Then alpha over beta minus q is equal to rho, so alpha is equal to beta times q plus r, where r is beta times rho. And the norm of rho is the norm of beta times the modulus of rho squared, which is strictly less than the norm of beta because rho was smaller than 1. But notice near a corner, multiple lattice points are within a distance of 1. So the quotient isn't unique, and thus the remainder is not unique. And that's unlike what's happening in the ordinary integers. We can actually have several valid choices of quotient and remainder. And that's totally fine because all that we really needed here was existence of a quotient and remainder. Now let's see this with a concrete example. So let's take alpha to be 5 plus 3i and beta to be 2 plus I. And so we can do a similar calculation that we did on the board and see that that is equal to 13 over 5 plus 1 over 5 times I. Now if we look at that within a fundamental square, we'll see that there are 3 valid choices for quotient and remainder pairs. We have 5 plus 3i can be written as 2 plus I times 2 plus 1 plus I, or times 3 plus negative 1, or times 3 plus I plus negative 2i. And so we've got 3 possible quotients, 2, 3, and 3 plus I, and their respective remainders, 1 plus I, negative 1, and negative 2i. And here's the big picture. The existence of a remainder small enough is equivalent to alpha over beta being within 1 unit of any lattice point. But that's equivalent to being able to cover this plane by circles of radius 1 centered at every lattice point. And so let's draw a circle of radius 1 around every lattice point and observe that they overlap, covering the entire plane. There is no gaps. And that's the geometric global version of the division algorithm on Zi. Now let's move to the Eisenstein integers. And so omega is e to the 2 pi I over 3, like we said before, or that can be expanded as negative 1 plus the square root of negative 3 over 2. And here we can take the basis vectors for the lattice to be 1 and omega, and this generates a parallelogram lattice. And so we've got the same game here. Let's pick alpha and beta, look at alpha over beta inside a fundamental parallelogram. The worst case distance of alpha over beta from one of these lattice points is 1 over the square root of 3. Now that's still less than 1, so the algebra goes through the same way. We're always guaranteed to have a quotient and a remainder. Likely we'll have more than one choice of quotient and remainder pairs. Then if we zoom out and put a circle of radius 1 at every lattice point, we'll see that the circles cover the plane even more densely. And so z omega is Euclidean by this geometric interpretation. But now let's look at another ring. Let's look at z adjoining the square root of -5. Here the basis vectors are 1 and the square root of -5. The lattice points are spaced square root of 5 apart vertically, much further than before. Near the corners, things look fine. At least one distance is less than 1. But as we move towards the center of the rectangle, every distance exceeds 1. There is no lattice point close enough to produce a quotient and remainder pair. And if you zoom out, you can see this globally. When we draw the circles at every lattice point, there are gaps. The tall, skinny rectangles leave uncovered regions, and that's geometrically why z adjoining the square root of -5 is not Euclidean. It does not admit a quotient. It does not admit a division algorithm. Now let's look at a specific concrete example of division in the Eisenstein integers, z adjoin omega. And so let's just recall that we've got this setup where omega squared plus omega plus 1 is equal to 0. We in fact have a complex number version of omega, but all we really need is this defining equation right here in terms of the quadratic polynomial that it satisfies. Now you can pretty easily see that you also get omega cubed is equal to 1. You can either just use this quadratic polynomial and do some symbolic manipulation to it, or you can go back to the fact that omega is equal to e to the 2 pi I over 3, and you cube it and you pretty clearly get 1. Okay, so now what I'd like to do is, let's say we do division with remainder where we take alpha to be 7 plus 3 omega, and let's take beta to be 2 plus omega. Okay, so we're going to do the same kind of thing that we did in zi. So let's look at alpha over beta. So that's going to be 7 plus 3 omega over 2 plus omega. But now what we need to do is multiply the numerator and the denominator by the conjugate of the denominator. So you can check that the conjugate is 2 plus omega squared. And so that's going to be 2 plus omega squared here as well. You could use omega bar, but it's pretty easy to check that for omega as defining the Eisenstein integers, the conjugate is just equal to the square. Okay, so multiplying this out, what are you going to get? Well, after a pretty straightforward calculation, you'll see that you get 10 minus omega over 3. So we can write that as 10 over 3 minus 1/3 omega. But now let's observe that 10 over 3, well, that's approximately equal to 3 because it's just a little bit bigger than 9 over 3. And then 1 over 3 is fairly close to 0. And especially when we're trying to create a quotient and remainder, there's a lot of rounding that goes on. So we can think about this as being approximately equal to 3. So that means you might want to start your guess with a quotient of 3 and just see if that is valid. So notice that if we have a quotient of 3, we're going to have a remainder of alpha minus beta q. We can always calculate the remainder if we have the quotient like this. And so that's going to be 7 plus 3 omega, and then minus, so let's see, beta times q, so that's going to be 3 times 2 plus omega. And so a pretty straightforward calculation will show that that is simply equal to 1. And so now we can write down our whole equation. We have 7 plus 3 omega is equal to 2 plus omega times 3 plus 1. And so we've got our quotient and our remainder. And our divisor is 2 plus omega. So what we need is the norm of our remainder to be less than the norm of our divisor, but that's pretty clear. Notice that the norm of the remainder, which is just 1, is 1. And then the norm of the divisor, you can calculate that to be 3. And 3 is pretty clearly less than 1, so we're good to go there. Okay, so there's an explicit example of division with remainder in z omega. Now, let's observe that we just saw that there is no division with remainder. In other words, there's no division algorithm inside of z adjoin root minus 5. So now, maybe as a bit of an exercise for you, you can find a pair of numbers where when you divide them, you do not get a reasonable quotient and remainder. In other words, it's impossible to get a remainder small enough. But instead of doing that here, what I'd like to do is look at some downstream effects of z adjoining the square root of minus 5 not having a division algorithm. And this is a classic example. Let's start with the number 6. And let's observe that we can factor 6 as 2 times 3. And both of these numbers, 2 and 3, are irreducible. And what I mean by irreducible is they do not factor into smaller parts in z adjoin root minus 5. You actually have to do a little bit of arithmetic to check that, but it's not so hard. But we can likewise factor 6 as 1 plus the square root of minus 5 times 1 minus the square root of minus 5. I think it's pretty clear that that factorization works as well. And furthermore, these two numbers are also irreducible. Again, you would have to check that, but it's not so hard to prove that those are also irreducible. So what we've done here is we factored 6 two different ways using two different pairs of irreducible numbers. But if you think back to the integers, in the integers you learn about unique factorization into primes. And so here we're calling these irreducibles and not primes because we in fact do not have unique factorization inside of z adjoining root minus 5. And that's in some ways a downstream effect of the fact that there's no division algorithm in z adjoining root minus 5. The easiest way to show that there is unique factorization is starting with the division algorithm and proving a cascade of results that eventually gets you to unique factorization. That being said, that's not the only way to prove that there is unique factorization. There are some exotic examples of rings where you don't have a division algorithm, but you do indeed have unique factorization. It's just, this is not one of those. We'll actually mention one of those later in the video. And now what I'd like to do is dive deeper into other quadratic extensions of the integers and explore when they have or do not have the division algorithm. Thanks for sticking around this long into the video. If you're enjoying the video, make sure and give it a thumbs up. And if you're not yet subscribed, consider subscribing. It really helps out. Okay, so now I'd like to look at the following question. If we've got a natural number d, when does this extension z adjoining the square root of minus d have the division algorithm? And I'm going to impose this condition that the division algorithm is occurring with the standard Euclidean norm. And that is that the norm of a plus b times the square root of minus d is a squared plus d times b squared. So that's the norm that it's inheriting from being within the complex plane. Now, the answer to this is fairly geometric. So let's observe that if we have alpha and beta in this space, so z adjoining the square root of minus d, then that means that alpha over beta will be somewhere in the complex plane and it will lie in a rectangle that has vertices in this space right here. So let's build such a rectangle right now. So let's say we've got the upper vertex left is here. Let's say we have the upper vertex right is there. The lower left is here, and then the lower right is here. And so, like I said, we should be able to land this alpha over beta somewhere here. And so, as we saw in the video or in the animation, kind of the worst place that you can land is right in the middle of one of these rectangles. So I'll just label this with alpha over beta. And well, let's say that this vertex right here is gamma, Let's say that this is gamma plus 1 because this is along the real direction. Up here will be gamma plus the square root of minus d because that's along the imaginary direction. And then here we'll have gamma plus 1 plus the square root of minus d because we're kind of like at a diagonal from the original starting point. Now we can put a little outline there as well. Now, since I put this thing right in the center, the measurement to any of these vertices should be the same. So I might as well say that the measurement is going to go to that vertex. But let's observe that since it's exactly in the middle here, that means that finding this measurement is the same thing as finding the hypotenuse of the following triangle. So we've got gamma plus 1/2 there because it's right in the middle, and then gamma plus the square root of minus d over 2 there because, again, we're right in the middle. And we'll need this distance, or the distance squared, to be less than 1. Well, notice that we can find the distance squared here pretty easy. And that's because if we fill this out, we've got a length here of 1/2, and the height will be given by the square root of d over 2. Notice it's not the square root of minus d over 2 because we're measuring a distance here. But now, like I said, we need that hypotenuse to have a length of less than 1. In other words, we need the square of that hypotenuse to have length less than 1. We can calculate the square of the length of the hypotenuse pretty easily. Notice that that's going to be 1/4 plus d over 4. In other words, it's going to be 1 plus d over 4. Like I said, we need that to be less than 1, which via a pretty simple calculation, we'll see that that means that d is less than 3. Let's observe that we assumed at the get-go that d was bigger than or equal to 1. That means that the only cases when we get division with remainder using the Euclidean norm, in other words, we have a norm Euclidean domain. So the only cases when that occurs is when d is equal to 1 or 2. But now the eagle-eyed among you might notice that we had something involving the square root of minus 3, but that was with the Eisenstein integers. Let's recall that z omega was equal to z adjoin 1 plus the square root of minus 3 over 2. You might say, well, omega was negative 1 plus the square root of minus 3 over 2. Well, notice that we can just add 1 to that and we achieve the following complex number. And let's note that this space right here, this z omega, or z adjoin 1 plus the square root of 3 over 2, is actually a further extension of the integers. And so the integers live inside of z adjoin the square root of minus 3, but in turn, this z adjoin the square root of minus 3 lives inside of z adjoin 1 plus the square root of minus 3 over 2. And so in the case of the Eisenstein integers, we were able to not just stop at z adjoin the square root of minus 3, but actually extend it a little bit further to land in a location, this set right here, aka the Eisenstein integers, where we in fact did have division with remainder. So the question that we have now is, can we always do this? And there's actually a fairly simple exploratory calculation which will tell us exactly when we are able to do this. Like, perhaps we should just do this with z adjoin the square root of minus 5, get a bigger space, and that bigger space would have the division algorithm. But as we'll see, that will be impossible. And so if we have a ring of the form z adjoin 1 plus the square root of minus d over 2, then it's going to be closed under addition and multiplication. And so that means we should be able to take this element that we're extending it by, multiply it to itself, and land back in the ring. And so what I really mean by that is I should be able to do 1 plus the square root of minus d over 2 square it, land back here. But that means I should be able to write that as a plus b times 1 plus the square root of minus d over 2, because everything in the ring is of that form. But we'll see pretty quickly that that's going to be impossible just via a simple calculation. So let's multiply everything out here. So multiplying out the left-hand side, we'll see that that turns into 1 minus d plus 2 times the square root of minus d over 4. So I'll let you do the calculation, but that's pretty straightforward. And then putting everything on the right-hand side into a fraction where the denominator is 4, we see that that's going to be 4a plus 2 times b plus 2 times b times the square root of minus d all over 4. Okay, great. But now let's observe we can just equate coefficients. So notice that the coefficient of minus d in the numerator here is 2, and here it's equal to 2 times b. So that tells us that we must have b equal to 1. But also we need the real parts to be the same. So we need this 1 minus d to be equal to this 4a plus 2b. So in other words, we're going to need 1 minus d to be equal to 4a plus 2, because we just observed that b had to be equal to 1. But now let's observe that that is equivalent to saying that d is congruent to 3 modulo 4. In other words, when we divide d by 4, we get a remainder of 3. So that brings us to the following summary. If d is either congruent to 1 or 2 mod 4, then that means that z adjoined the square root of minus d is the correct extension of the integers to look at. And that's because it's impossible to extend it further using this strategy right here, because you are not closed under multiplication. Notice that that covers this z adjoined the square root of minus 5 case, because 5 is congruent to 1 mod 4. So we were in fact not able to extend that set further in order to produce some division with remainder. But now in the case that d is congruent to 3 mod 4, well, we are able to do a further extension, which is really good news, because if d is congruent to 3 mod 4, then this thing is never going to have the division algorithm by our calculation over here without doing this type of extension. And here we would use 1 plus the square root of minus d over 2. And in fact, the big result here is that we get a division algorithm using the Euclidean norm. In other words, we get a norm Euclidean domain if and only if d comes from the following set. And that's going to be 1, 2, 3, 7, and 11. So notice that 1 and 2 are going to be just of this form right here, z adjoined the square root of minus d. But since all the rest of those are bigger than 3, they have to be of the other form. So 3, 7, and 11 will be like this thing right here, z adjoined 1 plus the square root of minus d over 2. Okay, so let's see the geometry that underpins this result. So the case when d is equal to 1, that's simply the Gaussian integers, which as we saw before was a square lattice. And here the circles comfortably cover the plane, and our worst case distance from any lattice point is 1 over the square root of 2. But remember that our norm was the distance squared, so our worst case is a half. Now if d is equal to 2, that means that we're looking at z adjoined the square root of minus 2, we get taller rectangles. And so after covering by circles, it's a little bit tighter, but everything is still covered. And our worst case distance squared in this case is 3/4, which is still less than 1. Now we already made the argument that said that rectangles fail for d that are bigger than or equal to 3, but the ring of integers can have a tighter lattice, a parallelogram and not a rectangle. And so if d is equal to 3, that is equal to the Eisenstein integers as we saw before. And in here, the worst case distance squared is 1/3. That's in fact the tightest of all of these packings. Now if d is equal to 7, the parallelogram is wider. The circles barely overlap, but we're still okay. And then when d is equal to 11, the circles are even less dense, but they still barely overlap. Let's look how thin the overlapping is. One step further and it might break. And now finally at d equals 19, it breaks. The parallelogram is too wide. The circles cannot reach and gaps appear. This is actually a famous example that we alluded to earlier. Z adjoin 1 plus the square root of minus 19 over 2 is something called a principal ideal domain, which means it has unique factorization, but there is no division algorithm. Now, what we just showed is that there's no division algorithm using the Euclidean norm, but in fact, there is no division algorithm at all. This is one of the most well-known examples of a principal ideal domain that is not a Euclidean domain. And so that gives us 5 values where we get a normed Euclidean domain, and that is d equals 1, 2, 3, 7, and 11, and that's the complete list. So suspiciously missing from our discussion today is what about real extensions? So let's look at those a little bit. And so if d is congruent to 2 or 3 mod 4, the correct extension to look at is z adjoin the square root of d. And the norm in this case has this hyperbolic flavor to it. The norm of a plus b square root d is a squared minus d times b squared. And that's got to be in an absolute value because we've got a subtraction there. And now if d is congruent to 1 mod 4, then you have this z adjoin 1 plus the square root of d over 2. And I won't write down the norm for this because the examples that we'll look at will be z adjoin square root of d, like this first case. So in particular, I'd like to dive kind of deeply into z adjoin the square root of 2. And so that means that my norm, so the norm of a plus b root 2 is going to be equal to the absolute value of a squared minus 2 times b squared. Now, something weird that happens here that doesn't happen in the imaginary extension case is you get infinitely many things that have a multiplicative inverse. Let's observe that if we take 1 plus the square root of 2 and multiply it by negative 1 plus the square root of 2, if we multiply that out, we get the number 1. But let's observe that that's equivalent to saying that the multiplicative inverse, 1 plus the square root of negative 2 inverse, is equal to negative 1 plus the square root of 2. But in fact, there are infinitely many of these, and we can grab infinitely many of these simply by taking this defining equation right here to the second power, the third power, the fourth power, so on and so forth. So just as a quick highlight of this, 3 plus the square, 2 times the square root of 2 times 3 minus 2 root 2 is equal to 1, meaning that those are going to be inverse pairs. And then one more, 7 plus 5 times the square root of 2, and then negative 7 plus 5 times the square root of 2 is also 1. So those are inverse pairs as well. Now, this is like kind of interesting just because these numbers that end up having norm 1, because if you have a multiplicative inverse, your norm has to be 1. And this is how this norm in these spaces completely diverges from our normal interpretation of size. So 1 plus the square root of 2 is approximately equal to 2.41. 3 plus 2 root 2 is approximately equal to 5.83. And this 7 plus 5 root 2 is approximately equal to 14.07. And like I said, you can grab infinitely many of these just by raising them to higher and higher exponents. So even though our norm, our measurement device that we will be using will always give us 1 for these, the actual size as a real number is getting bigger and bigger and bigger. Okay, so now let's look at a particular example where we might do division with remainder. So let's take alpha to be 7 plus 3 times the square root of 2. And then let's take beta to be negative 5 plus 4 times the square root of 2. Now, this is going to be a fairly similar calculation to what we saw before. So that means we're going to take alpha over beta. That's going to be 7 plus 3 root 2 over negative 5 plus 4 root 2. Now we'll multiply the numerator and the denominator by something that'll turn the denominator into a positive whole number. And so in this case, that'll be 5 plus 4 times the square root of 2. Now, a pretty straightforward calculation will land that on 59 over 7 plus 43 over 7 times the square root of 2. Now, we're going to play a pretty similar game to what we did with all of those other cases. And so notice that 59 over 7 is going to be between 8 and 9. Whereas 43 over 7 is going to be between 6 and 7. And then you can reason to say that 59 over 7 is closer to 8 than 9. And 43 over 7 is closer to 6 than 7. Now that's a little bit dangerous here because this closeness that we used intuitively was just a Euclidean distance. But like I said, we are not using a Euclidean norm here. So perhaps this wouldn't be the right choice, but as we'll see, this almost all of the time will work out. And so that means that we could take our quotient to be 8 plus 6 times the square root of 2. And then doing our calculation, so our remainder will be alpha minus beta times q. And again, like doing the arithmetic here, you'll see that this is minus 1 plus the square root of 2. Now we can finally write down our whole equation. So 7 plus 3 root 2 is going to be equal to minus 5 plus 4 root 2, so that's beta, times the quotient, which is 8 plus 6 root 2, plus the remainder, which is negative 1 plus the square root of 2. But now let's notice that the norm of our remainder is equal to 1. You can easily check that the norm of the remainder is 1 using our norm function right here. But then the norm of our beta in this case is equal to 7. Again, that's pretty easy to check using our norm function. And so we do have the remainder being smaller than the divisor, which is a necessity in this case. And now that we've looked at one of these real extensions, that opens up the question as to, is there some sort of geometry that's underpinning this existence of a division algorithm, like there is in the case of an extension by a non-real number? So even though all of these extensions are completely contained in the real numbers, you can embed them into R2 and just interpret the norm in a careful way. And so let's take a lattice for z adjoining the square root of 2. This is going to build a rectangular grid in the plane, just like in the imaginary case. But the norm is not x squared plus y squared. It's the absolute value of x squared minus y squared. A plus becomes a minus. And so let's revisit what happened when we divided. So let's take an alpha and a beta. Then we'll drop alpha over beta into a fundamental rectangle and watch the hyperbolic norms to each corner. At the center, that's the worst case. And here the norm is only 1/4, which is well under 1. And so that means we'll always be close enough to have a quotient and a remainder. If we slide the point around, we can find a position where 4 different lattice points are valid quotients, not just one. So again, the quotient is not unique, but it exists, and that's what matters. Now in Zi, the norm being less than 1 carved out a circle. Here it carves out a hyperbolic cross, a region between 2 hyperbolas. Now we can draw one around every lattice point and observe that they overlap, covering the entire plane. And so this covering of the entire plane by these hyperbolic crosses will imply that z adjoining root 2 is Euclidean. But not every real quadratic extension of the integers passes this test. So let's start with z adjoining the square root of 14. We have the same idea, but it's a much wider lattice. We can drop alpha over beta in, And observe that as we slide alpha over beta inside of a fundamental rectangle, we'll observe that there is often no valid remainder. We are often farther than distance 1 from one of these lattice points, meaning we're outside of the hyperbolic crosses centered at these 4 lattice points. But in fact, that's not enough here because of the weird geometry. We'd actually have to check that this is outside of the hyperbolic cross from any lattice point. Now, if we zoom out, fill the plane with these hyperbolic crosses, and then zoom back in, by visual inspection, it does look like there is an uncovered portion of the plane. Now, this uncovered portion of the plane does not mean that we lack a division algorithm, because it could be possible that a quotient of 2 elements in z adjoin root minus 14 never happens in one of these spots. But let's give an explicit example where this goes wrong. Before we look at our example with no quotient and remainder, I'd like to tell you about my second channel math major, which has full lecture courses in mostly upper division math classes. And in fact, this video here was inspired by one of the classes I'm teaching, ring theory, which has a full lecture course on that channel. And so, in fact, I'm really happy to be able to keep that channel ad-free thanks to my support on Patreon and via channel memberships. So if you'd like to help me keep that channel ad-free, consider becoming a patron or joining the channel. But now let's get back to this example. So, like I said, now we're going to do an example in z adjoin the square root of 14 where there is no quotient and remainder pair, and we actually don't have to try too hard. We can take alpha to be 1 plus the square root of 14, and we can take beta just to be equal to 2. And now we're going to do this towards a contradiction. So by way of contradiction, let's suppose we have 2 numbers. I'll call them Q and R. And so those are going to be in z adjoin the square root of 14 with alpha is equal to beta Q plus R, and the norm of R is strictly less than the norm of beta. Recall that that's what we needed for this division algorithm to occur. And we're taking this like standard norm as described up here. Okay, so now let's just introduce a little bit of notation here. Let's take Q and write it as A plus B times the square root of 14. And let's take R and let's write it as C plus D times the square root of 14. And observe that our equation over here, our alpha equals beta Q plus R, now turns into 1 plus the square root of 14 equals 2 times A plus B root 14 plus C plus D root 14. Now, the idea will be to expand out the right-hand side and then recollect the integer parts and the square root of 14 parts. And so that's going to be 2a plus c, and then plus 2b plus d times the square root of 14. So let's see, that means that 2a plus c has got to be equal to 1, and that means that 2b plus d also has to be equal to 1, because there's obviously a phantom 1 right there. So pretty quickly that tells us that c has to be 1 minus 2 times a, and d has to be 1 minus 2 times b. Now, furthermore, we're going to need the norm of R to be less than the norm of beta. So notice that the norm of R is going to be the absolute value of c squared minus 14d squared, and the norm of beta, that's the norm of 2, that's just equal to 4. But now we can put this version of c and this version of d in here. So that'll mean that 2a minus 1 quantity squared minus 14 times 2b minus 1 squared has got to come from the set 0, plus minus 1, plus minus 2, and plus minus 3. Because of course, if we take the absolute value, we want to land on something that's strictly less than 4, that gives us those possibilities. But now let's observe that this 2a minus 1 squared is an odd number. 14 times this will be an even number. So that means the left-hand side is an odd number. But that means that we cannot have this thing equal to 0 or plus minus 2. So next up, what I'd like to do is reduce this whole thing mod 8, keeping in mind that now we know that this is either plus minus 1 or plus minus 3. So using the fact that every odd number square is 1 mod 8, that's pretty easy to prove. So that means this 2a minus 1 squared is 1 mod 8. This 2b minus 1 squared is also 1 mod 8. Then that means that this left-hand side of the equation is congruent to 3 modulo 8. But that means that we cannot have this case right here of plus minus 1, because plus minus 1 is either 1 or 7 mod 8. And we can't have this negative portion here. We can only have 3. So now let's loop that back in and observe that now we know that 2a minus 1 squared minus 14 times 2b minus 1 squared actually has to be equal to 3. But now let's reduce this thing modulo 7. So let's say this blue arrow means we're reducing this thing mod 7. So 14 is a multiple of 7, so that will be 0. So that means we get 2a minus 1 squared is congruent to 3 modulo 7. But now we can make a quick chart over here of the perfect squares mod 7, and we'll see that in fact this is impossible. 3 is not a perfect square mod 7. So we can do that by looking at the numbers 0, plus minus 1 mod 7, plus minus 2 mod 7, and plus minus 3 mod 7. So we don't need 4, 5, or 6 because those are covered in our plus minus, and since we're squaring, the minus sign disappears or whatever. So let's see. If we square 0, we get 0. Square plus minus 1, we get 1. Square plus minus 2, we get 4. Square plus minus 3, we get 9. 9 is 2 mod 7. So 3 is not in that list over there, meaning there is no solution to this last congruence. And so that brings us to a contradiction, contradicting our ability to choose an appropriate quotient and remainder. So here are the big results underpinning everything that we've seen today. So the ring of integers of q adjoin the square root of d. So that's just a fancy way of saying z adjoin the square root of d if d is 2 or 3 mod 4, and z adjoin 1 plus root d over 2 if d is 1 mod 4. Okay, so this space is norm Euclidean. In other words, it has the division algorithm with the standard norm if and only if d is in this set of numbers. So we looked at some pictures for d equals negative 11 up to 3, but it's in fact norm Euclidean in all of the rest of those cases as well. But interestingly enough, z adjoin square root of 14 and z adjoin 1 plus square root of 69 over 2 are the only known non-norm Euclidean domains. And so what we mean by that is that there is a division algorithm, but it's just with some other norm. Now, this first result was from Harper in 2004, and the second is from Clark in 1994. And in the video today, we actually explored why the normal norm does not work in this square root of 14 case. And that's a good place to stop.